In this video we cover the first part of section 14.1. In this chapter we will do a calculus of multivariable functions, and we start with defining a function of several variables, and then similar like calculus 1 we're going to start investigating these functions. What is their domain, what is their range. In section 14.1 we will introduce the idea of level curves, and then we'll move on to finding the derivatives. Here the idea of derivative in multivariable functions, especially functions depending on two variables, is going to be much more interesting than the one in single variable calculus. And then in chapter 15 we'll deal with integrals of in two variables, in three variables, and so on and so on. Okay, so let's start from the beginning and let's just define what a function of what a multivariable function is. A function of two variables is a rule that assigns to each ordered pair of real numbers x, y in a set D a unique real number denoted by z is equal to f of x, y. Okay, the set D is called the domain of f, and its range is the set of all the values of f that f takes on. That is to say, f of x such that the ordered part x, y belongs to the domain D. Okay. If we define the function of three variables, then it's going to be a rule that assigns to each ordered pair x, y, z in the domain a unique real number denoted by f of x, y, z. Okay, so that means that the output is going to be in 4 dimensions, and we will talk about situations like this later on. Okay, now compare the domain in a function of two variables, right? It's consisted of all the ordered pairs x and y. What does that mean? That means that now the domain is going to be spread out into 2 dimensions compared to the domain in a single variable calculus where we will have found it on a line, right? Okay, so let's start. We'll discuss this more and more as we're doing these examples. So let's find and sketch the domain of, and now we'll list following functions. The first one is f of x, y is equal to square root of x plus y. Okay, just for the beginning, compare this to the function g of x that is equal to square root of x. Okay, everybody knows what the domain of this function is. X is greater or equal to 0. So when I say where the function g of x lives, right? In other words, I mean what values of x, only one variable, can g take, right? So on the real line, it's going to be the domain is consisted of all the values from 0 going towards infinity. Because of this equality sign, that means 0 is included in the domain also. Okay, but now when we talk about a function of two variables, right, we'll have to find the domain in the plane, in the xy plane. Okay, just keep in mind that a function of three variables, right, its graph is going to be something like this, right? Not of this particular function, of any function in 3 dimensions is going to exist in 3 dimensions, which means you find the domain in the xy plane. Okay, so let's see how we're going to find that for this particular function. Well, square root of, when the square root can be defined when x plus y can be greater or equal to 0. So how are we going to find this? Okay, so these are the values where x is greater or equal to y. Sorry, negative y. Okay, there is an easier way to sketch this function. First of all, let's sketch x is equal to negative y. Okay, so x and y. This is the line x is equal to negative y. And now take any point in the xy plane. Any point in the xy plane that doesn't depend on this, that doesn't belong to this line. Let's say the point 2 and 2 and 3. This point here, 2, 3. Does this point satisfy this inequality? Well, 2 is 2, x is equal to 2, is greater than negative 3. So this point belongs to the domain, which means the domain of our function are all of these xy points, right? And now check the inequality. It's greater or equal, x plus y is greater or equal to 0. That means that this line is also part of the domain, right? This function belongs also to the domain. Okay, so as you can see, any point that you can take here will satisfy this inequality. Okay, and then how much is going to be the range? Well, the range of the function, so let's say z is equal to f of x, y, and we know that z can take only positive values, including 0, right? Square root of any positive value is a positive value, so z belongs to the interval from 0 to infinity. Okay, it is important here to know that in multivariable calculus, no matter whether the function is of 2 variables, 3 variables, and so on, the output, right, f of x, y, f of x, y, z, f of x, y, z, w, and so on, the output is always going to be one-dimensional, okay? And the domain will have as many dimensions as the function has unknowns, okay? So let's see the second example. Square root of x times y, okay? So again, what is the domain of this function? The domain of this function are all the numbers x, y that satisfy this inequality. Okay, so when would this be satisfied? Well, this would be satisfied if x is greater or equal to 0 and y is greater or equal to 0, right? Or x is less or equal to 0 and y is less or equal to 0, right? So product of two positive numbers is positive and product of two negative numbers is also positive, right? Okay, because this is greater or equal to 0, the values on the axis are also going to be part of the domain. So the domain is where are spread out in the quadrants where x is greater than 0 and y is greater than 0. That's the first quadrant. So all the points here, and the quadrant where y is less or equal to 0 and z is equal to 0. And those are the points in the third quadrant. Okay, as I said, because this is greater or equal to 0, the axes themselves are going to be part of the domain. Okay, here again, f of x, y, or the z values will take on all the positive values. In the third example, again, still we deal with the square root function. So here I have square root of let me just square root of y minus x squared. Okay, so here y minus x squared has to be greater or equal to 0. Okay, so let's see how we're going to find the domain of this function. Well, we know how to sketch y is equal to x squared. Okay, so let's do that. X and y, and the function y is equal to x squared is just a parabola y is equal to x squared. So again, take any point either here or here and check whether that point satisfies this inequality. Okay, so let's take the point 2 and negative 1. Does this point satisfy this inequality? So negative 1 minus 2 squared is 4, so negative 1 minus 4 is not greater than 0. That means that none of the points on this side of the curve belong to the domain. Okay, none of the points in the xy plane. Okay, just to confirm, let's take a point here, let's say 0 and 5. 5 minus 0 squared is 5. 5 is greater or equal to 0, so obviously this is the domain of the given function, right? Because it is greater or equal to 0, right? Here, all the points on this graph satisfy the inequality y is equal to x, which means that this difference is going to be exactly 0. So on points on this boundary, any points on this, let's call it boundary, satisfy the equality here, right? That means that the domain of this function are going to be all the points, including the points on the curve itself. Okay, z here is the same, takes only the positive values, right? So for example, when would z be 0? Z or f of xy is always going to be 0 for any point, for any ordered pair taken on the curve y is equal to x squared. Okay. So, okay. Next exercise is find the domain of the function y is equal to x squared plus y squared minus 4. Okay. First of all, what is the function? The function is the ln function, so this expression here has to be what? X squared plus y squared minus 4 has to be strictly greater than 0, because the ln function is not defined at 0. Okay? Or in other words, x squared plus y squared has to be strictly greater than 4. So how to express this domain in terms of something that we know, that we are slightly more comfortable with? Well, we're comfortable with the equation x squared plus y squared is equal to 4, right? We have talked about this equation quite a lot, especially this semester, right? It's what is the center, sorry, it's the circle with radius 2 centered at the origin, right? Okay. Okay, so again, take any point here, and in this case, the origin, the curve doesn't cross through the origin, so why don't we simply check whether the origin satisfies this inequality? Okay, so 0 for x plus 0 for y, it's not greater than 4. That means none of the points within the circle will satisfy this inequality, right? If you take the point 3 and 0, right? 3 squared plus 0 is 9, is greater than 4, which means the domain is going to stay, is going to be consisted of all the points that are staying outside of the, on the exterior of the circle. But now, for the first time, we deal with strict inequality. So how are we going to deal with that? Be careful. This here gives us the circle with radius 2. So any point satisfying this equation belongs here, right? Which means any point on this circle will not satisfy this inequality because this is a strict inequality. So how do we do that? We're going to take out that circle. So the circle itself is not part of the domain. It's not part of the domain. So the domain are all the points outside of the circle, and the points on the circle are excluded of the domain also. Okay, what about the range now? Well, we know that z, right, if a function is defined as ln of something, right, the graph of ln takes on, the range of ln takes all the values from negative infinity to positive infinity. For example, as ln, let's say ln of w, limit as w goes to 0, this limit is equal to negative infinity, right, from the right, okay? Which means that if we are coming close, for any points that are here very close to this circle, they're coming extremely infinitely close to this circle, right, this expression here will go towards 0, right? And because of this squared, it's going to go to 0 from the right. So for any points approaching the circle infinitely close, the function f of x, y will go to negative infinity, right? Which means that the z value takes on all the real numbers. And the last example, f of xy being equal to arccosine of y minus x squared. Okay, so recall in single variable calculus that the arccosine function lives between -1 and 1. Right, so this is arccosine of x is equal to y, and this is the value pi over 2 and the value negative pi over 2. Okay, which means that this expression here, y minus x squared, has to be bounded by -1 and 1, has to be between -1 and 1. Okay, well, how to solve that? Well, that means that bring x squared on both sides. So here I have 1, or simply add x squared for the whole inequality, 1 plus x squared, and here -1 plus x squared, that's x squared plus 1, sorry, minus 1, my bad. Okay, so how are we going to sketch this? So these two inequalities satisfying. Why satisfying these two inequalities? Okay, so again, we are in the domain is spread out through the xy plane. Okay, so first 1 plus x squared is what? Is the parabola of x squared just shifted for 1 unit up. This is y is equal to 1 plus x squared, and 1 x squared minus 1 is the parabola x squared shifted for 1 unit down, right? So this is -1. Okay, so So as you can see, now these are two inequalities, and they separate the xy plane into three areas, right? This one here, this one in between the curves, and this one here, which is below the x squared. So this is y is equal to x squared minus 1, and the third area below the graph of x squared minus 1. So how are we going to do that? Again, choose a point, and choose a point whose x and y coordinates will satisfy both inequalities. Okay, so let's take the origin as the easiest one, because that one doesn't belong to any of the curve. Y is 0, so when x is 0, 0 minus 1 is less than y is 0, right? So satisfies the first inequality. What about the second inequality? Y is 0 is less or equal to 1 plus x is 0. So it satisfies both inequalities. So this point satisfies both inequalities. So that means the domain is going to be, this is going to be the domain. You can make sure, if that's the case, you can check the point whether the point 0, 2 satisfies this inequality, while you have a 0 minus 1 is 0 is less than 2, right? So yes, this point satisfies this inequality, but 2, it doesn't satisfy this inequality, because 2 is less or equal to 1 plus 0, and that is not correct. 2 is not less than 1, right? So you can always check whether this, the third area here, is satisfied, and you will see that it's not. So the domain is defined as this. Okay, and again, at the end, just make sure whether this is inequality, strict inequality or not. So in our case, the boundary is also going to be part of the domain. All of these points are also going to be part of the domain. This is the point -1 and 0, and this is the point 1 and 0. Okay, here the range is going to be, well, we know that arccosine function is bounded between -pi/2 and pi/2. So in our case, z is going to belong from -pi/2 to pi/2. And the last example that we're going to do, we're going to try to attack or try to find a function, domain of a function defined in 3 variables. Okay, so let's call the function f of x, y, z is equal to ln of 16 minus 4x squared minus 4y squared minus z squared. Okay, again, what is the domain of this function? The domain of this function is what? Are all the points x, y, z, so be careful, I'm talking about the domain, are all the points x, y, z that satisfy this inequality? 16 minus x, 4x squared minus 4y squared minus z squared has to be strictly positive, strict inequality. Okay, or that means that 16 has to be greater than 4x squared plus 4y squared plus z squared. Okay, so the graph of this function is going to be four-dimensional graph, and there is no way that I can sketch it, and I cannot even imagine how it is going to look in 4 dimensions. But with the second part of this video, we'll learn about level curves that will give us some kind of idea how to think about these functions. But what is going to be its domain? Look at this. Now the domain is going to live, it's not going to be spread out in the xy plane. It's going to be spread out in the xyz space, right? The domain is going to be 3-dimensional. Okay, so how are we going to find the domain? Well, you can always set up this equality. 16 is equal to 4x squared plus 4y squared plus z squared. And if you remember, these quadratic surfaces divide everywhere by 4. You get 4 is equal to x squared plus y squared plus z squared over 4 or over 2 squared. And this was an equation of a ellipsoid. So and this is 1, negative 1, 1 and negative 1. So and then here it's 2 and negative 2. Okay, so this is negative 1 and 1. This is 1 and negative 1 and 2 and negative 2. Okay, so now choose any point and check whether it satisfies this inequality. Now look at this. This ellipsoid doesn't pass through the origin. So I can easily check whether the origin satisfies this inequality. So 16 is definitely greater than 0, right? Which means that the domain of this function are going to be all the points inside of the ellipsoid, right? Inside of this ellipsoid, the interior of this ellipsoid. But be careful, because it's a strict inequality. The shell of the ellipsoid is not going to be part of the domain.